Think about how Claude Code or other modern agent frameworks tackle a hard problem. They spawn multiple sub-agents, each chews on the problem independently, and then an orchestrator stitches the results together into a final answer. It works remarkably well, but if you peel back the layers of skills, memory modules, and tool routing, you start wondering what is actually doing the heavy lifting. Is it the elaborate scaffolding, or is there something simpler underneath that the model itself is doing? That is the question the authors of HeavySkill set out to answer, and their claim is provocative. The magic of agentic harnesses can be distilled into a two-stage capability that lives inside the model's own parameters. No fancy orchestration required. The motivation here is that the agent ecosystem has gotten complicated fast. We have orchestrators, planners, memory caches, skill libraries, tool routers, and the relationships between them are often bespoke. Prior work on parallel reasoning has tried various tricks, like inserting special inline tags into the chain of thought so the model branches and merges its own reasoning, or hard-coding synchronization points, where multiple thought streams have to compare notes. Other approaches use Monte Carlo tree search style exploration. The trouble with these is they require either architectural surgery on the model, custom training recipes, or rigid scheduling that does not adapt to how the reasoning is actually going. The authors argue that frameworks like Kimi K2 and Pakor have stumbled onto something cleaner, which is a clean two-phase decomposition. Think in parallel, then deliberate sequentially over what you came up with. So here is the core method. Given a problem, the first stage uses a language model to generate k independent reasoning trajectories. Think of these as k different students, all attacking the same exam question without talking to each other. Each trajectory contains both the internal chain of thought and a proposed answer. Then comes the second stage, sequential deliberation, where a second language model, which can be the same model or a different one, reads all those trajectories and produces a synthesized final answer. To make this work within context length limits, the authors introduce what they call a serialized memory cache. Since each raw trajectory might be enormous, they prune trajectories down and shuffle their order to prevent the deliberating model from developing positional biases, like always trusting the first answer it sees. The deliberation model is prompted to classify the query type, critically evaluate each thinker's reasoning rather than just count votes, and even rederive the answer from scratch if it judges all the thinkers to be wrong. There is also an optional iterative deliberation mode where you feed the deliberation output back into the cache and run another round, similar to how a person might keep refining an argument by revisiting earlier drafts. And here is the clever packaging move. Rather than implementing this as a Python pipeline that lives outside the model, the authors distill the whole protocol into a single readable skill document, a plain text specification with 4 parts, namely a deliberation prompt template, output format constraints, activation conditions describing when to fire up heavy thinking versus stay quiet for simple queries, and a parallel reasoning protocol telling the orchestrator how to spawn subagents. Because it is just text, the same skill file works across Claude Code, custom harnesses, or anywhere else that supports skill loading. The reasoning capability becomes portable, decoupled from any specific infrastructure. Now, to the metrics, because they matter for understanding what the experiments show. Mean at k is the average accuracy across the k parallel trajectories, a baseline. Pass at k is whether at least one of the k trajectories got it right, which represents the ceiling of what the model could possibly achieve if you had a perfect picker. Vote at k is majority voting, the standard best of n approach. The authors introduce heavy mean at k, which is the average accuracy of the deliberated summaries, and heavy pass at k, the ceiling across deliberated summaries. The hoped-for hierarchy is that heavy mean beats vote beats plain mean, and ideally, heavy pass approaches or exceeds the raw pass at k ceiling. Across a long list of models, from GPT-5, Thinking to Claude 4.5, to DeepSeek R1, and Kimi K2, plus open weight models like Qwen 3 and the R1 distillations, the pattern holds up well on STEM benchmarks like IME 25, Beyond AMI, HMMT, and GPQA Diamond. Heavy mean consistently beats mean and frequently beats majority voting too. With strong frontier models, the heavy pass metric sometimes exceeds the raw pass at K, meaning the deliberation phase is not just picking the best trajectory, but synthesizing across them to produce answers that no single trajectory contained. For example, on the IMO answer benchmark, GLM 4.6 hits a heavy pass of 86% versus a raw pass of around 75%. That is a meaningful gap, and it suggests the deliberation is doing real cross-trajectory reasoning. One nice diagnostic experiment looks at queries where the parallel pass rate was below 0.5, the regime where majority voting would fail because the correct answer is in the minority. Even there, heavy thinking rescues over 5 in out of about 1,400 queries, showing the deliberator can identify correct minority answers rather than just following the herd. There are some intriguing findings worth flagging. First, the deliberation model does not need to be a stronger reasoner than the parallel thinkers. When the authors pair R1 distill Qwen 7b as the parallel reasoner with Qwen 2.5 32b, instruct as the deliberator, the larger model helps even though on its own, it scores much lower on AIME than the smaller specialized reasoner. The skill needed for deliberation is comprehension and synthesis, not raw reasoning horsepower. Second, on subjective tasks like Arena Hard, the gains shrink or even go slightly negative because deliberation optimizes toward a kind of correctness-oriented mean that may wash out the stylistic individuality reward model's favor. Third, iterating the deliberation loop beyond a single pass shows a curious split. Heavy mean keeps creeping up with more iterations, but heavy pass actually degrades, suggesting that later iterations introduce confirmation bias from earlier outputs and shrink the diversity of the exploration space. So more iteration is not unambiguously better. The limitations are worth being honest about. The approach is inference expensive since you are running K parallel trajectories plus one or more deliberation passes. The paper does not deeply quantify cost-performance trade-offs against simpler test time scaling. The diversity of parallel trajectories is critical, and if your model collapses to similar outputs, deliberation has nothing to synthesize. The deliberator can also be misled when all the thinkers are confidently wrong, and the prompt-level instruction to rederive from scratch is a band-aid. And while the authors gesture at using RLVR to train the heavy thinking skill directly into the model, the paper does not present a full training recipe, just the framing that this should be possible. The broader thesis that complex agent harnesses are basically dressed-up versions of parallel, then summarize, is compelling, but may oversimplify cases where genuine tool use, long-horizon planning, or multi-turn state actually matter. Now, let's walk through some questions you might have after hearing all of this. First, why does deliberation outperform majority voting, given that voting also looks at all K trajectories? The key is that voting only sees the final answers as opaque tokens and picks the most common one, which fails whenever the correct answer is a minority opinion. Deliberation, by contrast, reads the full reasoning chains and can evaluate which arguments are actually sound. So when 6 thinkers make the same arithmetic slip and 2 get it right, voting picks the wrong answer, while a careful deliberator can spot the slip and side with the minority. Second, why can a weaker model serve as a competent deliberator? Because deliberation is closer to a reading comprehension and synthesis task than a from-scratch reasoning task. The hard cognitive work of generating candidate solutions has already been done by the parallel thinkers, so the deliberator mostly needs to compare, critique, and combine. This is similar to how a good editor does not need to be a better writer than the authors they edit. They just need strong judgment. It also suggests a practical decoupling, where you spend your most expensive reasoning model on the parallel stage and a cheaper instruction-tuned model on the synthesis stage. Third, why does iterative deliberation help the mean but hurt the ceiling? When you feed an earlier summary back as context, the model anchors on the conclusions it already reached. That anchoring nudges later iterations toward the previously favored answer, which often is correct, raising the average. But it simultaneously shrinks exploration, so the rare cases where the first deliberation missed a clever synthesis are no longer recoverable in later passes, which lowers the ceiling. It is the classic exploit versus explore trade-off playing out within a single inference pipeline. For large-scale recommendation systems, the most immediate application is in the slow, expensive parts of the stack where quality matters more than latency, like offline candidate generation for high-value users, editorial curation pipelines, or LLM-based ranker explanations and reasoning chains. You could run parallel reasoning across multiple ranking criteria, say relevance, diversity, freshness, and long-term engagement, and then deliberate to produce a synthesized ranking justification, which both improves quality and yields auditable reasoning traces for compliance. The decoupling insight is particularly practical. Use a strong reasoning model to generate candidate user intent interpretations or item rationales in parallel. Then, a cheaper, faster model for the deliberation step, which keeps serving costs manageable. The portable skill packaging is also worth taking seriously for production. If heavy thinking is a plain text document rather than an architectural choice, you can roll it out incrementally across your LLM-driven surfaces, from query understanding to cold start item descriptions to personalized notification generation without rebuilding infrastructure. And the finding that deliberation can identify minority-correct answers maps directly to a recurring problem in recommendations, namely, surfacing high-quality long-tail items that majority signals would bury. Using deliberation-style synthesis over multiple ranking trajectories could systematically rescue good candidates that simple ensemble voting would miss, which is exactly the kind of win that compounds across billions of impressions.